So what we're going to do today, more explicitly, is to go through these resampling methods, and we're also going to discuss the central limit theorem, and we're going to show a demonstration of the central limit theorem and why this is of importance for methods like Bootstrap, which is a resampling method, and what is the basic philosophy behind many of these resampling methods. And the typical methods which we will focus on are the Bootstrap and cross-validation. Now, I just wanted to give you some small messages. I know that many of you have been mailing me, and this is in particular people who are not at UIO and want to attend the course remotely because you have a full-time job or and so on. So I'm going to respond to many of you a little bit later, but for most of you, there's no problem in actually following the course. We should have space enough. So if you are in a situation where you attend remotely due to work or whatever, I mean, there shouldn't be any problem in downloading the lectures and downloading the videos and follow them. So as I said, the videos of the lectures, they are more kind of raw dump of what was said during the lecture. So you can think of that as a kind of podcast with the images, but it's not of the how to say, of Hollywood quality, if you. However, I hope they can be of some use. I also wanted, and talking about videos, there's actually a fantastic set of lectures by Brunton and Kotz online, and these are really high quality videos, and I am very, very envious of what they have achieved. Actually, they have a pretty fancy blackboard you can write on. I don't know if you watched some of these videos. They have videos on the SVD, for instance, which are just excellent, and I recommend them. So there's a link down here, and you can actually get straight into their teaching material. So you should have the link on the slides. Any questions before we move on about practicalities or other topics? Okay, so what I'm going to do now is just to jump back to the whiteboard, and we are going to slowly step ourselves through the central limit theorem, and we are going to use that one to look at the implementation of the Bootstrap method. So the main theme this week is resampling methods and statistical analysis. Statistical analysis of the data. Just to repeat, the overarching motivation behind the usage of these resampling techniques is that in most cases, you have a limited set of data. And that means that your statistics is going to reflect the limited set of data which you have. Because one, you normally do not have the probability distribution for the different events, even if we have assumed that many of these are stochastic events. Two, sometimes, even if you have it, it could be almost impossible to make a simulation because the statistical distribution or the probability distribution may be a multi-dimensional beast, which is actually quite time-consuming when it comes to producing probabilities or even calculating expectation values. So what we are normally confined to is to calculate what's called the sample mean value or the sample expectation value. And that is directly linked with the number of data you have. So the kind of expectation values we will calculate may not be equal to the ideal ones if somebody were to give you the probability distribution. So these resampling techniques actually weigh to compensate for that. So that when you make an estimate of the mean squared error, or you make an estimate of the mean value or the variance of a quantity, what you can then tell an eventual user of the model is that this is the best I could do. So you will also see that some of these resampling techniques may actually be very sensitive to the way you actually do the resampling. And we are going to see some examples with cross-validation where the results you get for the mean square error will actually be sensitive to the way you partition your data. So there's a lot in machine learning. We do have methods, we do have the tools, but there's a lot of trial and error where you're tweaking parameters and rerunning things just to see what can give you the best fit to the data. So there's not that you can a priori say that if I do cross-validation with 10 folds, I'm going to get an optimal result. You will actually have to play around and study the sensitivity of your results based on these different parameters. And as we move on, you will also see that there will be more and more parameters which we can tweak. Some more important, some less important. But let's now look at the first intermediate step. There's a small step which we need, and that is the so-called central limit theorem. So this is a very important limit in statistics because it states that you can, if you assume that your events are identically distributed and independent, and you have a probability distribution, which you don't know, but you know the mean values of these, then you can actually, in the limit of a huge data set, you can actually show that the probability of all the data which you have is going to approximate a Gaussian or a normal distribution. And that's a very powerful statement. And that's one of the statements which lies behind some of the implementations of the bootstrap method. And so we're going to go through the theorem first. And then after we've done that, we're going to look at demonstrations so that we are not going to prove that the bootstrap actually gives what it says, but we're going to do numerical demonstrations of it. Actually, to prove that requires some semesters in statistics. So I hope you can just accept what's in the literature. So let's look at the central limit theorem. So what you could think of now is that we have a series of experiments. So assume now that you have a set of data, and these data, they are given by a probability distribution which reflects the fact that these are independent and identically distributed. A set of data of IIDs, events or stochastic variables of events. And you could think of now you running an experiment every day for many, many days on. And when you run these experiments, let's say today, I guess all of you have a lot of spare time problems, so you can run such experiments in evenings. I guess nobody's doing anything in evenings. So you could then produce a mean value, and then next day you repeat the same thing. So suppose now that you run one such experiment, and this experiment has a mean value x of I, so that's a set of experiments, experiment xi. So this could be day I when you run that specific experiment. And that's going to have a mean value, and ideally there is a probability distribution if this is a discrete probability, which is given by a discrete set of events. This has a probability distribution P, which we know. But now we're simply assuming that these are independent and identically distributed events. So just for simplicity now, I'm going to let this xi, the expectation value, I'm going to let that one go over to an x of I. So I hope that's not going to cause confusions, but I'm just introducing that for the mere sake of simplicity. Then, what you could think of now is that you run a series of such experiments. And then you can, when you compute that, you would have a total mean, which is now given by the means from every experiment. And this goes up to day m. And then you simply divide this by m here. Does that sound okay? So every x is one given experiment you run, and that has, you have extracted a mean value. So the total mean, this set, would then be simply a double sum, the sum over all the experiments you run, and a sum over all the individual ones every single day. So we know the distribution, so the x of i's, or these x's, x of i's, they follow, or they're the outcome, they follow a distribution which we know, px of I. Or actually p of x, I'm just going to take away the x of I here. Then the question is, what form does p of z take? And I'm going to put that into an uppercase letter. So suppose now you do these experiments many, many times. Then you can ask yourself, I mean, what kind of distribution are these experiments moving towards? So what the theorem says is that this distribution is going to be a Gaussian. It's going to be a Gaussian with the same mean value as every individual experiment, but it's going to have a variance which is different from the variance of the single experiments. And that's an important statement here, because it affects immediately the way we do bootstrapping, for instance. It has immediate consequences for that, as you will see in an example. Now then, we can construct such a probability by, for obtaining an average z, is as assuming that we have a product of all the individual probabilities. Since these are independent variables, that means that we can set up the total probability as a product of the individual probabilities. So that's a kind of statement which some of you may have seen in courses in statistics. And we actually use that one in the product rule, and also it's used in Bayes' theorem if we have independent variables. So what we can do then is actually to construct this probability with a constraint that the mean value should be z. So this probability then is something which would be the product of all the individual ones, but now we're putting in a constraint. So we have a d of x2, of p of x2, and this goes up to the last experiment which we run, of p of x of m. But then we have a so-called delta function where we have z, so we have a constraint, and that's the one which is going to give us the product of the probabilities with the correct constraint. So this is one way to build up the probability p of z. Minus, and then we have x1 plus x2 plus x of m divided by m here. So I hope you can forgive me if I assume that you've seen the delta function before. So we, as physicists, we half jokingly say this is the way Dirac entered the annals of mathematics, because it was Dirac who actually came up with these distributions. Okay, so this is just a way we can now set up the constraint that z has to be these mean values, and then we have the product of the identical distributions. Then what we can do next is actually to compute these integrals, but then what we need is a formula which defines the delta function. So the delta function comes in many different disguises, and there are tons of these equations which are pretty handy sometimes. And the one we are going to use is this definition of a delta function of 2 pi, and then there's an integral from minus infinity of a dq of the exponential, and then we have an I of q, and this is multiplied with z minus x1 plus up to xm divided by n and end of parenthesis. Then what I'm going to do now is to define a quantity for these x's and I'm just going to call these for mu. So since these are identically distributed and independent variables, they have all the same mean value mu. Okay? And I can then insert just one, and I can insert in the integral for the function of pz, I can insert minus I times q minus I minus mu times q. It just gives 1. And then we have an expression for this p of z, which is going to be equal to 1 over 2 pi minus infinity to plus infinity, and then I have a dq of v of iq, and then I have z minus mu. So I'm just reshuffling terms in the equations here. And this is multiplied by an integral minus infinity to plus infinity. And remember now that these are identically distributed, so that means that every event should have the same expectation values here, or the same probabilities as well. So we have an e of I of q, and then I have a mu minus x, and this is divided by m. And you can easily see that this has to be exponentiated to n. So the integral which you see here is the one which is, the last one is the one which is of interest now, and which is the one which is going to show us that we are going to move towards a Gaussian distribution. So if I look at the integral of dx of p of x here, of e to the iq of mu minus x divided by m here, this is something which I can calculate by simply using a Taylor expansion of the exponential. So I would have a d of x of p of x, and then I obviously have 1, and then I get plus I times q, and then I have mu minus x divided by m, and this goes on as I get a plus, and then I have a minus, so this is actually a minus, because I have I squared, so that gives me minus, and then I have a q squared, a mu minus x squared, divided by 2m squared, and plus plus. Now, I just want to give you a small hint here. So we have defined this d of x, p of x, times x, that's given by this quantity mu, and these integrals are normalized, or the probabilities are normalized, to 1. So if you look at the first term, what should that give us? Just 1. So normally I expect 0 when I ask these kind of questions, but this time it's actually 1. If you look at the second term, on the other hand, so we had 1. So I may do this in an alternative way. I love zeros, but now we have 1s. What about the second term? That's 0. So it's 0. So I'm back to 0. So the second term is 0. And you see that immediately because mu is a constant. And then we are integrating over x. And since we have the definition of mu as the mean value, so then we have just a mean value minus a mean value. And mu is a constant. So when we integrate here, we have a constant times dx p of x, which is 1, times the constant. So the second term becomes 0. If you look at the third term, on the other hand, so any good suggestions there? If you look at the definition of there's another quantity. So the mean value, yeah, that's the variance. So what we can do now is simply to rewrite this integral in terms of, so we can rewrite this in terms of 1 minus, and then we have this q squared, and then I have a sigma squared, so this is my variance, divided by 2m squared, and then I have this plus plus plus. Now I can actually insert this quantity which you see here. If you look at this quantity, I can now insert that quantity back into the integral here. and then I have to perform that integral as well. Now, this means dealing with the complex arguments, so I'm just going to give you the answer, because else it would take me a little bit more time here. So the most important thing for us is actually to see where the mean value comes from, where the variance comes from, and what you can show then when you calculate this integral here as well, and that one, is the following. So what you get then is that this P of Z is then given by 1 divided by the square root of 2 pi, and then I have this sigma squared divided by m, and then this is multiplied by E of minus, and then I have Z minus mu squared, and then I have 2 times sigma squared divided by m. So remember now that the variance of a single x, that is given by P of x multiplied with the x minus mu squared d of x, and that's a quantity which we would simply call the variance. So what you notice now is that due to the normal distribution is that this variance of z is actually given by sigma squared divided by m. And that means that the standard deviation, ST dev, is equal to sigma divided by square root of m. And that's one of the standard results which you may encounter in statistics texts. So we are having a Gaussian distribution which has the same variance as the single distribution we started with, but divided with the square root of experiments which we make. So clearly when you make now this number of experiments larger and larger, the variance of this distribution is going to be narrower and narrower. So this is a very important result, and it affects the way we are going to think when we do bootstrapping now. So what I want to do is actually to switch over to an example where we have actually implemented the bootstrap algorithm. And then we are going to demonstrate the central limit theorem. So the theorem is extremely powerful because we have not specified P of x. So we just left it unspecified, except that the only thing we said is that P of the x's are independent and identically distributed variables. That's the only thing we have assumed. So we may not know P of P of x. We can calculate the mean value, we can calculate the sample mean, we can calculate the sample variance, but we may not know the value. But if we have plenty of data, we should be able to reach a Gaussian distribution. But this applies only if these are identically distributed and independent variables, because else I could not have calculated that integral. So that's an important assumption. So not all distribution P of x actually give this limit. Okay, so let's go back to the Jupyter notebook now and take a look at the simulations of this using the bootstrap method here. So let me just bring that up. So this is in the lecture slides for this week. And just to remind you quickly, when we defined the bootstrap yesterday, is that what we are doing then is that we are simply drawing numbers from a distribution eventually. And we are doing that by randomly picking. Actually, yesterday I said we reshuffle randomly and then we picked randomly. We pick randomly, we don't reshuffle. So we pick randomly with replacement, which means that we can have the same data point popping up again. And in the bootstrap, so let's look at this example here, and then we're going to go back to the notebook, to the whiteboard. So this is an example where I now am defining a data set which has a mean value of 100 and a standard deviation of 15. So I have 10,000 data points, and I produce a normally distributed data points. So what I'm doing now is simply to construct a Gaussian distribution with mean value of 100. This is my data, and I have 10,000 data points, okay? So when I calculate the mean value, I should get something close to 100. What you will see is that since you have a limited set of numbers, you're not going to get 100. You will get something close to 100. And I should get a standard deviation, which is 15. So if I call the standard statistics package, which you have in NumPy, I should get these numbers, right? Because that's what I feed in the definition. But you will not get exactly 15, and you will not get exactly 100. And you will see that from the simulation. Then I'm doing bootstrap. And I'm going to do bootstrap as many times as I have data. So as a kind of rule of thumb, there's no kind of magic number of how many bootstrap resamplings you're going to do. So you can do as many as you have data points. You can do a fraction of it, let's say 1%, 10%. This is something which you have to play around with. So many practitioners do as many bootstraps as they have data. That's one practice, but there's nothing magic behind these ways of doing it. So if you run this code now, what you will see is that I have my bootstrap method coded here, so it's pretty simple. And this function randint, as you can see here, picks randomly data in my data file. So I'm transferring my data file here, and it picks randomly the numbers with replacement. So the number of numbers which I pick from the table is n. And when I run it now, what you're going to see is that in this specific case, you can see the original is not exactly 100. It's close to 15. But then you see now when I've done the bootstrap, and I've done the bootstrap 10,000 times. So if you take this number here, and you do the bootstrap, this is standard deviation, 15. If I do the bootstrap 10,000 times, what should I get? So it's 15 divided by the square root of 10,000. Maybe I'm offending you because the answer is on the slides there. You should get 0.15, right? So what you're seeing now is that what the bootstrap is doing is actually doing what the central limit theorem says. So I started with the normal distribution. So every single bootstrap which I do produces one P of X and one specific mean value. And then I collect all the 10,000 mean values and obviously divide by 10,000. And then I should get the same. So the mean value never changes with these resampling techniques. But what you see here is that you are producing another distribution. And if you then plot the distribution, because with these numbers, you can now make a histogram. So if I plot it, it looks like this. So what you see now is that your mean is not exactly 100. Actually, 100 is here. But instead of having a standard deviation of 15, you see now that the distribution has gotten more narrow. The original one had one standard deviation of 15, so that has quite a big spread. Now, as you're making more and more experiments, you're actually narrowing down the standard deviation. And that means that hopefully you are getting a better and better evaluation of the mean value. So previously, you had a mean, which was given by 100 plus minus 15. Now, when you have run these experiments many, many times, you have a mean value, which is still 15, but plus minus 0.15. That's one standard deviation. If you want to do so-called two confidence intervals, which means a confidence of 95%, then you would have 100 plus minus 2 times 0.15. That would give you a confidence of 95%. So these are simple examples of the central limit theorem, but it's also a simple implementation of the bootstrap method. So as I said, the bootstrap is extremely simple. You pick new data, and then you keep calculating the observable you want. And at the end, you'd simply take the average of all the samples you've done. So let's repeat a little bit about the bootstrap and set up the different steps. You may think, why should we do this? Because with Python, I had just this function wrapped in here where I can pick this randomly. But let's put up the steps now for the sake of completeness. Any questions to this demonstration? Yeah?
Why isn't the mean of the Gaussian the same as the mean that you set?
Because I have a limited number of data points. So if I put in 100,000, so let's go back. This is going to take time. So if I take 100,000 here, and let's just let this run in the background. So this is going to take a little bit more time. And I'm going to, in the meantime, look at the bootstrap algorithm. And I'm not, while we wait, I'm not going to tell one of my lame jokes, promise. So let's, and according to my wife, I only know of one joke. Let's now go back to the bootstrap method, and let's set up the some of the basic steps which we have when we do it. So the bootstrap resampling is pretty simple. So what we would have an original sample. And we can call this for a domain D of data. And let's just say that this contains z0, like we did yesterday, up to some z of n minus 1 here. And then the first step is to compute a bootstrap sample, which means that we pick randomly with replacement these different data points, which means that we can actually pick the same point several times, draw a bootstrap sample. And what we would have then would be a D, and I'm going to call this D1 star. So this is going to be a Z0 star, a Z1 star, and all the way up to Zn minus 1 star here. And then I compute some property here. So this could be something like the mean value. So suppose now I want to compute the mean value, and this is going to be the mean value of one of these samples. I have n, and it's going to be a sum over all the I0 up to n minus 1 of the set i's star. So it doesn't need to be the mean value. It could be another quantity. But let's suppose we take the mean value. You can replace this with a general function. Then what we would do next is simply to repeat this b times as we did in the program. And that yields an estimates, and this yields estimates, yielding estimates. So I'm going to have a theta 1, I'm going to have a theta 2, up to some theta b. So this is the number of times I did the bootstrapping. Then what I can do now is to calculate the mean value of these observables, or these estimates which I've calculated. And then I would have a sum over j equal 1 up to b of theta of j. So suppose this is the mean value, which is one of the quantities you most likely will calculate, and we are going to do that when we are looking at the bias variance trade-off. So the next step then is that we would compute, or we can compute, we don't need to do it, but we can compute the variance. So that could be something like S squared, 1 divided by B, and then I have a sum from j equal 1 up to the number of bootstraps samples, which I did. I take my theta j, which is the data set which I have for a given measurements, and then I subtract the mean value, which I calculated, and this is squared. And then we could then output this S squared and theta. That's just one possibility, other functions you want to calculate. And the theorem, what it shows, the bootstrap method, so the bootstrap method, you can actually prove that. And that was done in follow-up papers by Efron, who actually developed the method first, is actually the bootstrap that shows that you can approach the true variance and the true mean. It approaches the true mean and the true variance and other observables and other expectation values. So this theorem is then, or this method, this bootstrap method, is then used to actually produce reliable estimates of, let's say, your mean squared error. So your mean squared error is also an expectation value. It's a sample expectation value, and the bootstrap method is a method which then, when applied repeatedly, allows you to calculate an mean value of the expectation value based on the mean values or the mean square errors for every single bootstrap sample which you do. So if you look at what I put up here, I put up the mean value, but there's nothing which hinders you in calculating other functions for every bootstrap sample. Then every bootstrap sample gives you an expectation value, and at the end you collect all these values and you produce a mean value, or a mean value of all these expected values you calculated. And that's the essence of the bootstrap method. And you can actually show that if you know, you can actually run simple tests like the one we've been doing with the normal distribution here. And you see that the bootstrap method actually brings you closer and closer to what you expect. And that's a very useful method, and it works extremely well when you have identically distributed and independent variables. There are extensions to non-IID data, but we are not going to cover that because one of the basic assumptions we often make in many of these machine learning algorithms, like here in linear regression, is actually that the data are IIDs. That means independent and identically distributed. That's an assumption we made from the very beginning. So let's now move over to what's called the bias-variance trade-off, which is one of these important features in machine learning, which people normally use to understand whether you're overfitting or underfitting. And it's also used in order to assess which is the best model. We are coming back later after the break to features like model assessment and model selection, because these are also important questions when we are running calculations. And in project number 1, you're actually running many models. So you have polynomials to different degrees, and then at some point you have to assess which is the best model. And these are things which we need to discuss a little bit more in detail. But the next topic which we are going to look at now is this bias-variance trade-off, And after the break, I'm going to set up the equations or derive them. But now we are simply going to look at the mean squared error, which we have defined as 1 over n, and we have a sum of I equals 0 to n minus 1. And we have a model, which is given by the y tilde. And this is the quantity which we typically would present when we are fitting a continuous function. Now, the bias variance trade-off says that we can rewrite this term in terms of a bias, where we now have the model here. So this depends on y of I, or just y, minus the mean value of y. So that's the model. And this quantity is squared plus the variance of the variable y itself, plus the noise which we have, this sigma squared, which follows from the assumption we made that y is given by a function, a deterministic function, f of x, a plain deterministic function. That's one of the assumptions we made, plus a noise term which is normally distributed, as we have been discussing again and again. And the variance of that term is this variance of epsilon is given by this quantity sigma squared. Now, after the break, we are going to see how we can get to this equation. But what I wanted to do now is just to sneak in a small demonstration before we take a break. And then after the demonstration, we are going to try to, demystify what is happening here. So let's go quickly back to the Jupyter notebook, and then we're going to step ourselves through the different details after the break here. Now, if you scroll down here, there is a simple example where I'm now setting up a fit to a function, and the function is now takes data of x from -3 to 3. This is a function you've seen many, many times, and you may ask, why is this guy always showing the same function? I know that there are other functions, but there is an element of human laziness, and this is a good function. It's has an e to the minus x squared, and it's easy to fit. So I'm only taking 40 points here, but I'm fitting a polynomial of degree 14. Actually, here I'm putting bootstrap to 100, but I could put it, so normally people put it actually less than number of data sets. Then I define my mean squared error, which is this quantity, my bias, my variance. I have a polynomial degree, and now pay attention to one thing. I do the splitting of the data in train and test before I do the bootstrapping, and before I have a loop over the polynomial degrees. So that means that my test data, they are the same test data for all models I'm going to make. And that's important. So you should think of the test data as something which stays in a vault and it's untouched. And then I do the training with different models on data which I'm going to bootstrap. So this is an important aspect. I mean, if you do the test inside the loop where you fit a model, you're actually going to have different test data every time. And then you're not comparing your model to the same data. So that's important to keep in mind. And it applies a lot. It's important for the project, actually. So here I just took the polynomial features. I didn't construct the design matrix. I actually set up just the data here, and then I let the scikit-learn set up the design matrix with the train data. So keep that in mind. That's the train data here. And do the linear regression on the train data. I even keep the intercept. And now what I'm doing for every polynomial degree, I perform a bootstrap. So I'm resampling here, x train and y train, every time. So the resample function is actually a function which allows you to do this bootstrapping with replacement. So that's another function which comes in handy in your project. And then I make a prediction. Thereafter, I'm computing the error. So this is the mean square error on the test data, because I'm not interested in the prediction I make on the train data, because as we said yesterday, the train data are going to be better and better behaved with increasing complexity. So that's not very interesting. What's interesting is actually how the model fares with respect to the test data. So every time I have a polynomial, after I've trained it, I'm going to make a prediction, and then I calculate the bias and the variance. And after the break, we're going to discuss a little bit more in detail, but if I run it, you're going to see something like this. So this is the mean squared error, and you see the mean squared error on the test data decreases to a polynomial of a certain degree. And then suddenly it goes up. So this, what you have here, is the variance of the model, and you see that increases, and that's a sign of overfitting. Your bias, on the other hand, just keeps decreasing. So what we want, as we discussed yesterday, we want a low bias and a low variance. And we are going back to the interpretations here. What is going on? What does it mean for us? And how can I use that to understand which is the best model? You should keep in mind that if I now change the data set, suppose I do 1,000 data, there is no overfitting problem. So everything we do is conditioned by the amount of data you have. So in this particular case, when I have 1,000 points, I have plenty of data. It's easy for me to generate new data all the time and repeat the experiments. And in this case, I would simply say, hey, a polynomial degree 14 is perfect. I can use that one. There's no point in going beyond because my mean squared error is now decreasing. It's getting smaller and smaller. So this is an example which is very important to keep in mind. You may not get the first figure I showed you when you're running your calculations. So in textbooks, it's always this kind of idealized case which you will see. And the curves always look very nice and smooth. In real life, they do not. So you would have to tweak, in order to see this kind of behavior in project one, you would have to tweak the number of data which you have. So if you have lots of data, you will probably never see this behavior where you run into overfitting. It's at the end, this is actually what matters, how much data you have. And ideally, all the methods we are discussing, they are what we call data greedy. The more, the better. Unfortunately, this is not always the case. Okay, I went a little bit over time, so I suggest that we meet back at 20 past the hour, right? Is that okay? And just feel free to ask questions. And okay, so the thing I wanted to discuss now, so after we went through this simple example, I wanted to go through the derivations of these equations and just to show you the basic elements which are needed and what kind of trick is being used to do that. And this is something which is also relevant for project number one, because you're being asked about the bias variance trade-off. And then we are going to go back to the codes again, and we're going to look at how to interpret these results here in terms of the bias and the variance trade-off. So let's move back to the whiteboard and do some of the derivations which are needed. So what we said is that the bias variance trade-off is a way which we can rewrite the mean squared error. So you will often see this kind of analysis in connection with the mean squared error and linear regression, or methods which use the mean squared error, because then you can really split things in terms of this bias and this variance. So the assumptions which we have are that the data sets Y, they are given by some function which we don't know and which we are making a model for, and then that we have some normally distributed noise. So these are some of the basic assumptions which we have. So in the beginning of project one, you were also asked to calculate some expectation values. And one of the things we have assumed in the model is that this f of x is a deterministic function. And that was reflected in the fact that our model which we made, so we actually make a model where we approximate this f of x of I. This is being approximated with this y of I tilde. So in general, we don't know y of I, or f of x. And that means that we have to make a model, and everything we are doing is actually a way to assess whether this model is good or not. That's the kind of more overarching theme or recurring theme which you will see again and again. Then in the exercises, what we found is that this E of y of I tilde is the same as y of I tilde. And we actually assume that this E, and if we now just write it out, and if you go into many textbooks on statistics, sometimes they would never write it as vectors, but you have to assume whether these are vectors or scalars. But this is equal to itself, so we normally say it's unbiased. And since the mean value of the noise is equal to 0, this is the same as the mean value of y. And then another thing which we had is that the variance of this noise which we had, epsilon, was simply given by this sigma squared. And that's the first part of the project. So what the bias variance trade-off is doing is actually a rewrite of the mean squared error in terms of 3 new terms, or one term is already known, which is the variance of the noise. So if we go back to the equation for the mean squared error, this is something which we wrote as the expectation value of y minus y tilde squared. Now, if we know the distribution for the y's, if we know this probability p, then what we would do then is to write the mean squared error, which then has a function dependence over the domain of events. This will be given by y minus y, and both y and y tilde depend on x. So there's a probability p of x, and I'm just looking at a very simple model. It could be multidimensional as well, because I have a domain D, and I haven't specified whether this is in one dimension or in many dimensions. But this will be the general expectation value for the quantity. So what I can do now is to actually rewrite this term. So this will be the same as an integral over y, and if I now put in the value for y, which is given by f, so I would have f plus epsilon minus y tilde squared of p of x d of x. So in case we have a continuous distribution, and we also assume that the function f of x is a continuous function. So that means that we can still keep these assumptions that there is a continuous distribution which describes the data. Then the next step is actually to add and subtract a term here. So what we do then in the integral is simply to add and subtract. And this is basically the trick which is needed for rewriting. And the things which you need, so we add and subtract the expected value of the model which we have, which we know how to calculate. We know that this is given by the design matrix times the parameters beta. So this is something which we can easily calculate. And then what we end up having to evaluate is simply this d, and then we have an f plus epsilon minus y tilde, and then we have plus e of y minus e of y, and squared of p of x of d of x. And then when we are looking at the squaring of these quantities, we have to keep in mind the sum of the expectation values. So remember now that the expectation value of the noise, you're going to get terms which will contain the noise term times some of the variables. Remember again that f is a non-deterministic variable. Yeah? Yeah, sorry. I forgot to put on the tilde. Thanks. It's always the same thing. You're watching your notes, and then you forget to transfer what's in your notes. So, human nature. Okay, and then you have to keep in mind also that the expectation value of this noise which we have added is defined to be equal to 0. We have the expectation value of y. We have the expectation value of f. So f is a deterministic function. So that means that when I square out things here, there will be terms which are identically equal to 0. And I end up with one term. So these are the only terms which are non-zero. So I'm going to get a term here, d, the integral, and I'm going to have f of x. And now I'm going to define here, just for the sake of simplicity, I'm going to just call this expectation value for mu of y tilde, just for simplicity. So you will get a term which now is given by minus mu of y tilde, and this is squared, multiplied with p of x, d of x. And then you have plus a new term, which is given by y of I tilde, or we should rather write y of x, since you're looking at continuous functions, y of x tilde minus mu of y of I tilde, p squared, p of x, d of x, plus just the variance of this term epsilon squared, and we know the value of that one. Now, the first term is the term which we would call the bias, because this says how much we miss the true data from our mean value. So this term is normally called the bias. The term which you see here is called the variance. So this is actually the variance. So this will be the variance of y tilde. And this is the variance of the noise, which we already know is something we put to a constant sigma squared. Now, what you see here is that there is a dependence on an unknown function f of x. So we don't have f of x, because if we had f of x, I wouldn't be here. There's no need for actually doing any fits, because we know the function. So f of x in all actual calculations is actually replaced by the data which we have. So this is the standard practice when you are going to evaluate this function. But formally, this is the way it stands, but we have to make an approximation when we want to evaluate something. And what you should also keep in mind is that we have a discrete data set. Discrete set. And we don't know p of x. So that means that we are going to look at sample expectation values. And this is the reason for resampling. So when you calculate it once, you will get an expectation value. But if you invoke then the central limit theorem, or if you perform bootstrapping or cross-validation, the hope is that you can then calculate expectation values again and again, and then you will take the average of these expectation values, and hopefully this is a better estimate with a smaller spread in uncertainty of the expectation values. So this follows very much the same thing which we discussed with the demonstration of the central limit theorem, that what we get is a distribution of the mean values. This is what we calculated in the examples before the break. But then when we increased the number of bootstraps, what we got then was a distribution with a narrower error, a smaller error. So that means that we could with some confidence say that the mean value should be in this small interval. So we started with a large spread, but then when we kept repeating it, the spread around the mean value got smaller and smaller and smaller. So that means that we could have some kind of confidence that this is the value you should get from the data set. And this is the point with resampling, because normally we don't have the luxury that we can generate more and more data. And in many, many calculations or in many, many experiments, you have only a few hundred data points. And that's why we end up doing these resampling techniques. So what happens then is that this mean square error, which we wrote out, so the MSE is something which we have estimated in the following way. So it's a sum over the data sets which we have of n minus 1, and then we have a y of I minus y of I tilde. We can now rewrite that one, and in principle this is an approximation because we don't know the exact function f of x. So I should have put an approximation sign, but I'm just going to put an equality sign here. So we're going to have this bias plus the variance. So we're going to have a 1 over n of I equals 0 up to n minus 1. And instead of the function f of x of I, we are now going to put in the mean value. And now I just rewrite the mean value of y tilde. So this is going to measure the kind of spread from the data points due to the mean value of the model, which we have settled on. So this is the bias term. So in actual calculation, this is what we end up evaluating. 1 over n, and then I have I equals 0 of n minus 1, and then I have y of I tilde minus the mean value squared. So this is the variance in the model itself. So variance of model plus this sigma squared, which comes from the random noise. And this is normally done on the test data. So in project number 1, when you're going to analyze the bias variance trade-off, the typical thing you will end up demonstrating it with is using Bootstrap, because that makes it very simple to place your data outside before you start doing the bootstrapping. So you can have the test data outside, you split it in train and test, and then your test data is something you can just leave out there, and then you easily run the bootstrap again and again with increasing model complexity. So if you look at the Jupyter Notebook again, so let's go back to that one. So, and this figure is actually good to take a look at when we now are going to discuss a little bit more what is going on. So if you look at the figure here, the typical situation, or what you ideally want, is that you want to have a low spread in your model. So that means that when you make a fit and you apply to the test data, so remember now that this is done on the test data. So the test data have not been included in the training. So it means that your test data, the variance there, should be small. You don't want to have a huge spread. If you have a huge spread, that means that your model is now either overfitting or underfitting. Normally it's overfitting. Then you want to have a low bias. So that means that the mean value of your model doesn't deviate from the data points you want. So the ideal situation is the one which you have in the upper left corner. When you have a high variance and a low bias, the typical situation is that you will get close to the target, but you will have a large spread. Alternatively, you may have a very low variance, but a high bias. So that means that your model doesn't have large deviations when you apply that to the test data, but you miss the point. That's the lower left figure. And then the one to the right, the lower to the right, is actually the typically unwanted situation. So let's go back a little bit to the simple case which we run. And let's look a little bit more into the details here. So this is something which is pretty close to what you end up doing in the project, except that now I've been using these polynomial features which are baked into scikit-learn. I'm keeping the intercept, as I said. And here, what I'm doing now, I'm looping over the polynomial degree. So every polynomial has a specific degree. And then I'm performing a bootstrap for every polynomial degree. And that gives me a prediction as a function of the model and the number of bootstraps. So every time I perform a bootstrap, I now make a prediction for y. So that the y is actually my data. So the y prediction is the model which I generate every time I do a bootstrap. And this is done on the test data. Okay? Then, when I perform the y prediction here, what I do now, I take y test. I don't have the exact function f of x. And that means that I replace that one with my data, my output, which is y test, and I subtract the prediction. So this is my mean squared error. And then when I calculate the bias, you can now see that I take my f of x is replaced by the y test here, and I calculate the mean of the prediction. And then for the variance, I calculated simply the variance of my prediction. And then I'm using these NumPy functions for calculating the variance. And then it's calculating the mean here, because then I'm actually calculating the mean value. So in order to obtain this variance, it just actually means a mean value here. And then what I get then is simply, at the end, is simply a plot. And you could then see a result like this. Or alternatively, if I now reduce this to something, as we saw here, 40 points here, and just rerun, then we got a figure like this. And there, if you now look at this bias variance trade-off, the way you're going to interpret these results is that, in a way, it summarizes this kind of tension in machine learning, and in particular in supervised learning, between the complexity of the model and the amount of training data which you have or which you can generate. And since data is often limited, it is often useful to use a less complex model with higher bias. That is a model whose asymptotic performance is worse than another model because it's easy to train and less sensitive to sampling noise arising from having a finite-sized training data set, which means a smaller variance. So if you look at the equations, what they tell us is that in order to minimize the expected test error, you need to select a statistical learning method that simultaneously achieves low bias and low variance. So these quantities are non-negative. Keep that in mind. So what do we mean by the variance and bias of a statistical method or learning method? The variance refers to the amount by which our model would change if we estimated it using a different training set. So if you go back to this simple picture here, I could now make a new model which could give me a lower variance. So this kind of variance, it measures the differences between different models. So that's an important aspect. Then, if you then, since the training data are used to fit the statistical method which you're dealing with, or the learning method, different training sets will result in a different estimate. But ideally, the estimate for the model should not vary too much between training sets. However, if the model has a high variance, then small changes in the training data can result in large changes in the model. And that's what you saw when I changed the training data. So when I went to 100 or 1,000 data points, as we did here, my model is exactly the same. So keep that in mind. It's a polynomial fit, but now I have much more data. And if I rerun that one, what happens then? If you look at the error and the bias variance trade-off, you see you basically have zero variance. So I'm actually doing a very good model development. My variance is basically zero. And I have a bias which is slowly moving to smaller and smaller values. So my variance in this case is basically zero. So that's an example of low variance. And then clearly you could continue with higher degrees of polynomials. So there's nothing which hinders you now to move on to, let's say, a polynomial of degree 30. And let's see if that still holds. So it's pretty quick to run these calculations, as you can see. Now, in this case, you still see now that there is a small tendency when you now reach a polynomial getting degree closer to 30, it seems now that the variance is creeping up a little bit. But you see again here that even now to a polynomial of degree 30 with 1,000 points, you're having a pretty low variance. So everything which you deal with is a trade-off between the number of data points and the complexity of your model. And this bias variance trade-off is a way to assess what is the optimal model. That's one of the ways of doing it. And if you look down a little bit in the slides, there's another example from scikit-learn here. So if we run that one, this is a simple example of overfitting and underfitting. So this is a case where we have a simple first-order polynomial to a data set which is described by a fourth-order polynomial. So if I do a straight line, this would be a clear example of underfitting, and you would have a pretty high bias. If you then have a degree 4, you're traversing the data excellently. When you now have a polynomial of degree 15, you see now that you actually, this is an example of overfitting. You're actually trying to traverse all the points, but your true function is actually the one which goes through here in the orange line. So this, the first one would be an example of underfitting. It would have a high bias. This would have a low bias, but an extremely high variance. And this would be the model which does the best fit, because we are fitting a fourth-order polynomial, and the true function is actually given by the orange line here. So this kind of analysis is one of the things we actually want you to do in the project. And coming back to these resampling methods, one of the reasons why we deal with them is simply because we want to make sure that we have good enough estimates of the bias, the variance, and the mean squared error. So if there are not any questions now, I'd like to move on to the last topic, which is another resampling method, which is called cross-validation. So cross-validation is one of the, one of the most used methods for doing this kind of resampling. So I want you also to think a little bit about things like, and we are coming back to this in the discussions, both of project one, but also during the lectures. So there are two a little bit subtle things before we move on now. So one is model selection, and the other one is model assessment. So basically everything we end up doing is having a model which we want to fit to the data. When you do model assessment, no, model selection, then you're going to estimate the performance of different models in order to choose the best one. So what you saw in these examples here, we now looked at the performance of this polynomial fit, and we found that for these specific polynomial fits, perhaps a 10th order polynomial is the best example. So what you also should think of, if you look back at this example which we had here, with a 30th order polynomial, this is something which becomes more time expensive to fit a 30th order polynomial with tons of points. So you also have to strike a balance between how many CPU cycles you want to spend and the quality of your model. So here you could say that, okay, it seems now that my mean squared error flattens out around a polynomial of degree 10. And if there is basically no change from a polynomial of degree 10 to a polynomial of degree 30, then you would stick with a polynomial of degree 10 because it's much cheaper to evaluate as well. So if you give somebody a fit with a polynomial of degree 30, and that person has to calculate function values from that, that's going to require a lot of floating point operations. So the simpler the model, often the better it is. So this is a kind of model selection which you have to make. Now, the kind of criteria I would use would typically be, if you're doing a fit like this one, it would be to analyze the bias variance trade-off on the test data and look at the mean squared error. Now, another thing which you need to think of also is to assess the quality of the model. So when you've chosen a model, you have to find one where you actually estimate a prediction error, and you want this prediction error to be reliable. And that's why we use these kind of resampling techniques. Now, one thing which is common to do when you do this kind of testing, because till now, we haven't said anything about ridge and lasso regression. So when you are running things with ridge and lasso regression, you have an additional complication in the hyperparameter lambda. So that means that you need to figure out which parameter lambda gives the best fit to the data. So you would run, if you now look at the fit which we did with ordinary least squares, we would have to repeat that, but for a series of values of lambda. And then for each lambda, you would assess whether my mean squared error is now of the quality which I can accept. And then you would say that at complexity, polynomial complexity of degree 10, I take lambda equal 10 to the minus 3. That's the one which gives the best value. Then you would move on to polynomial of degree 11, and then maybe lambda equal 10 to the minus 2 is the one which gives the best fit. So when you now increase the number of parameters from ordinary least squares to ridge and lasso, you need to consider the optimal value of lambda as well. So scikit-learn, for instance, has a grid search which allows you to actually find the optimal value. The alternative is just a brute force mesh grid search where you simply set up a set of points and then you pick those which give you the best results. That's a pretty standard brute force straightforward way, which I normally recommend in project number one. So later we are going to look at refinements to this kind of brute force scheme. So you have model selection and model assessment. And when you're assessing the model, you need also to think of these hyperparameters. And for ridge and lasso, they can actually drive your mean squared error to lower values than you would see with ordinary least squares. But this is something you need to play around with. So, yeah.
Since you said it might be weight as the model, would it be that you're better lambda that fits better for a degree 11, increase the variance?
It could happen. That could happen.
How would you take that?
So you would actually have to investigate these things. So you don't know these things a priori, whether a lambda which you have for a specific model complexity gives a larger variance or not. So you don't know that. So the unfortunate thing, we cannot tell a priori what is the best parameter. And that's why we have all these kind of steps with model selection, model assessment, and so on. Because people get disappointed when they realize, I thought this was just a fantastic thing, but what you end up doing at the end is just to tune parameters. It's not that bad. It's actually fun because there's a lot of insight about the functions you can gain from that. Okay, so what I wanted now at the end is actually to discuss a little bit another method, which is called cross-validation. So cross-validation is also a very simple method, and there are many, many different types of ways you can split the data. So the way you would do it, you would shuffle your data, and you would split the data in different groups. And for each unique group, you would decide which group to use as a set for test and which to use for a training data set. Then you would fit a model on the training set, and you would evaluate that on the test set. So every time you do that, you produce a mean squared error for the test. And then you repeat. So let me just draw this for you. It's actually pretty simple. So let's go back to the whiteboard and set up the way we do the cross-validation. And I see that I've been mumbling too much now. Hey guys, we're getting close to the hour, but let me just quickly put up the cross-validation, and then we are going to discuss that a little bit more next week as well. So suppose now that you have a simple data set. So this is cross-validation, CV. That's this shorthand which you will often see. Suppose we have a data set now which looks like this. X, 1, 2, 3, 4, 5, and 6. So I'm practicing with counting. So till recently, I would typically count 1, 2, 3 many, and now I got into 6 actually. So I could now split the data into different folds. So I could define something which is called K equal to 3, which is the number of folds. And then, with the number of folds, I could now split my data. So this is done randomly when I split the data. So fold 1 could now contain 5 and 2. Fold 2 could contain 1 and 3. And this fold 3 could contain 4 and 6. So what I could do now, when you do this, so you would have now slots like this. So the 1, 2, and 3. So this is fold 1, F1, F2, and F3. What I would do now is to split this into training and this into test. So let's suppose this is our first iteration. So the first step, then I would train and obtain an error on a mean squared error on the test data, which is this fold 3 here, okay? So I would now get a test error test. Could you say it again? Oh, okay. Yeah. It's okay. It's getting close to the end now. But let me just conclude this one, and then we just. So error test here would now be this error. Let's just call this error 1, and that contains the application of the model to this fold number 3. So this comes from fold 3. Then I would repeat now, and in the next case, what I would do is a new iteration, and now I would split F1, F2, and F3. And now I would use these as training, and this for test. So the error for the test now is the error which comes from fold 1. And finally, see the basic pattern here. It's pretty straightforward. Then the final step would be to have fold 1 and fold 3 for train, and this for train, and fold 2 would be the test fold. And then we would calculate the error on the test data, which would be the error of fold 2. And then the total error is then given by error of fold 1 plus error of fold 2 plus error of fold 3. And this is divided by the number of slots which I have now for testing and calculation and the calculation of the errors. So this will be 1/3. Now we can increase this k. So typical values for this number of folds is normally between 5 to 10. There is one type of a cross-validation where you just leave out one point for testing, and that's called just one out. So cross-validation with one out. And this becomes much more data intensive because you're doing this for all the data. So if you have 10,000 data points, you're going to calculate 10,000 errors. And this is going to be applied to just the one point which has been left out. So cross-validation is a kind of a way to resample the data where you split them in slots. And for every type of splitting here, you have a certain amount of data which runs into training and another type of data which is being used for testing. So next week, I'm going to recapitulate some of these things, take a look a little bit at the examples and the slides, and we will try to wrap this up on Thursday, but you should have more or less enough material now for jumping into the final part of project number 1, which deals with the statistical analysis. Feel free to ask questions as always, and also if there are things which are unclear, just shoot me an email or just discuss with us at the lab or after the lectures here. So in the meantime, best wishes for the weekend, and see you next week.
Når du gjør cross-validation, det noen forskjell på å velge bestemte grupper? Hvis du kjører det 3 ganger med test. Mye ting jeg glemmer.
Altså det tenker jeg om du bare kunne kjøre en feil testbit om igjen.
Ja.
Så det ble nesten som cross-validation.
Ja, det stemmer.
Det var nesten på. Ja. Det vi gjør cross-validation, det var låst forskning.
Ja. Men er det noe bedre?
Jeg vil ikke si nei. Men det som er tingen med cross-validation er at du har, hva skal du si?
Fordi hvis du velger den training-testen med 0,85, så vil det være det samme som det her. Og så gjør du det 3 ganger.
Ja. Så men det vanlige liksom at folk velger mellom 5 og 10 år. Og du vil se at i noen av resultatene spesielt hvis man ikke
Ja, men da kan det også bare variere.
Skal vise, hvis du har litt tid, så skal jeg vise et eksempel her. Og egentlig skal jeg ta og stoppe her nå, sånn at vi kan ta...
Ja, bare...
Nei, jeg tenkte på at